have 1 hour. Of course, I have 1 hour. So.
Yeah.
Okay, thank you very much, Irene, and it's always a pleasure to be here and to see your friends. So the title of the talk is Update on Nonlinear Potential Theory. And okay, an alternative title could be Linear and Nonlinear Calderon-Zygmund Theory, because actually the talk is about certain things that are classical in the linear setting and how they can be translated, how can they find an analog in the nonlinear one. Okay, so therefore, following the general path of Calderon-Zygmund theory, let me go to the first part, and let me start by the classics, because it's always nice to start by the classics. So Calderon-Zygmund theory actually means the following. So you assign a linear elliptic or parabolic equation. So you assign a datum, in this case we call it mu, and this is the most simple example, a paradigm that yet contains many of the features of that you can find in the more general setting. I mean, so you assign where the Laplacian is, and you want to retrieve possibly in a sharp way the differentiability and integrability properties of solutions, in this case of the second derivatives of the Hessian. So the sharp result is the following one, and this is one of the results we can come up with. When mu is equal to Q, then the Hessian is equal to Q, and this is consistent from a dimensional viewpoint because you're saying that the trace of the Hessian is equal to Q, and therefore you want to commute the trace into the whole Hessian. This can be done via singular integrals, as I'm going to recall now, apart from the borderline cases where it is shown to be false by counterexamples. Because, of course, this goes via double risk transforms that are not well behaving in L1 and L2. Okay, the idea is, therefore, you want to retrieve information on solutions. It's rather simple. Okay, let me recall the general approach to this, which is the following one. The general approach is, in this case, for this particular equation, is that you use a representation formula via a so-called fundamental solution, which is the so-called Green's function, which is this one. And of course, since you're interested in the Hessian, then you differentiate twice under the sign of integral, and then you come up with this guy. And now a problem occurs here, because you see that this kernel, let's concentrate for simplicity to the case, on the case n larger than 2, is integrable. When you differentiate it twice, it becomes non-integrable, because this 2 goes away after a couple of differentiations. So you come up with a kernel which is non-integrable. And now that's the point. The point is that although this guy is non-integrable, it enjoys subtle cancellation properties that allow to come up with a result. So let me disclose this in the next slides. So at this stage you define an associated operator. The operator sends mu, and mu at this stage, since you are interested in a priori estimates, then you can go to other cases by approximation, and it's simply or whatever. And then k is a second derivative of something that grows in general as 2 minus n. So therefore it grows like minus n. This means that the Fourier transform is bounded. So by Plancherel, this sends L2 to L2. So this is the easy part. But then cancellations come up here. Because although this guy is non-integrable, when you make a difference here, then it becomes integrable. This is a way to say that there are small cancellation properties. It's a way that Ormander eventually found after the usual, the first definitions by Calderon-Zygmund. It's one of the ways you may say that there are local cancellations. So the idea is that if you just consider this is plus infinity. If you put minus, then there are some things that are canceling. So the idea is very simple. It's when you teach basic calculus, you teach this in a poly, right? So this is the wrong way in this setting. You do not have to use this. You have to exploit that A and B can have cancellations. So that's essentially the same thing. This is probably, historically speaking, one of the main examples where cancellations come up. Then they became essentially, they are nowadays, it's nowadays common to see there are problems which are called critical problems. So situations where certain quantities which are usually bounded and estimated just by their size then become infinite. In all these situations, then you do not bound just by the size, you look for additional cancellations. This is typical, for instance, when you do consider harmonic mappings or variational problems with critical growth, exploiting the presence of some subtle conservation law, whatever. So it's a general paradigm in modern nonlinear analysis. So when size is not enough, look for cancellations. That's okay. Let me just point out that if you instead are looking only for the differentiability, for the integrability property of the gradients, then you just differentiate once under the sign of integral, and then you can just consider least fractional operators. These guys are integrable as long as beta is larger than 0, and therefore you can proceed avoiding cancellations, essentially because you are not in the critical situation where you are looking for maximum regularity. And this is essentially what I was telling before. A similar situation occurs with a similar problem. Now the right-hand side is in divergence form. Okay, and you come up with the following estimate, provided suitable boundary conditions are considered, of course. This is dimensionally speaking. The correct thing to do because the gradient goes as capital I. And the first year basic calculus students' proof is very simple: simplify divergence, and you get the result. Simplify divergence, you get the result. Actually, it's the same for this because since you are considering now this problem, you can use this representation formula where now you have this guy, right? Now G is x minus y, 2 minus n where n is larger than 2. Then you differentiate once, you come up with this first derivative. Then you get rid of divergence integrated by parts. And you once again come up with a simpler integral. That's okay. So dimensionally speaking, this is the correct thing because the right-hand side is in divergence form, so it's more irregular in some sense. Okay, a subsequent approach was found by Campanato and Stampato in the 60s, and it's an interpolation approach. It's an interpolation approach, and this interpolation approach can also be extended to nonlinear settings and to some nonlinear degenerate operators. I think it's essentially a work of Luke, I think at the beginning of the 70s, right? You had some nonlinear interpolation paper, right?
Yeah, I was not the first.
Okay, but in the linear case, Campanato and Stampato gave another approach. I mean, it's interesting to see what is the approach here, because they do not consider this representation formula. For instance, let me recall the approach for this problem. That's the problem I was talking about. So you define an operator that sends f into the gradient of the solution. F into the gradient because they enjoy the same thing. So just by testing the equation, it's a trivial thing. It's a one-line proof that T sends L2 into L2, and this is the corresponding factor of the Plancher L stuff that I told you before. Then, by regularity, you can prove that this guy sends L infinity into BMO. Okay, what is BMO? Okay, in general, it's not true that this guy sends L infinity into L infinity by counter seconds. So what is L infinity? What is BMO? BMO is a function space which is larger than L infinity, but close enough to L infinity to allow for interpolation. Sometimes its norm is flat enough to be close to L infinity and to allow for interpolation. And then they proved that if you have a sublinear, particularly in this case, linear operator sending L2 into L2 and L infinity into BMO, then the same operator sends LQ into LQ for every 2 larger than 2, and then you conclude by duality for the other values, Q. Okay, you may observe, you might think that here the idea of the study of cancellation has been skipped. It's actually not true, because since now this is an interpolation approach, the idea of cancellation has been shifted into the definition of the space, which is BMO now. BMO is essentially the space of functions which are integrable, such that this, let's say, mean square deviation, this is the average of f over a ball, is finite at every pole. So there are cancellations enough to allow this guy that is finite. So the use of cancellation has been shifted to the space. This is typical in mathematics. When you think you can skip one idea, then the idea or its ghost comes out somewhere else. You see, if f is in L infinity, this is trivially bounded by twice L infinity norm. Otherwise, you really have to look for cancellations. Okay, this is as long as the linear theory is concerned. And now let me go to the nonlinear theory. And now we have to distinguish between two cases. The first, okay, I'm going to consider quasi-linear elliptic operators of this type. You can go also to fully nonlinear, but in general, since I'm considering the general operators, this is a more delicate situation, and also parabolic situations. But let me concentrate on this model case. So you have an operator in divergence form. I can also consider systems, and H is a general distribution. The assumptions I'm going to consider are the following one. These are classical assumptions since the work of Lanchinski and Durrell from the 60s. Because when you do consider these assumptions are always something that is going to generalize some relevant model example you have in mind. And the relevant model example you have in mind is one given by the so-called P Laplacian, when P is larger than 2. It's this operator. I think I do not have to spend time to say why this operator is relevant in several situations. For instance, it's the Euler-Lagrange equation of the functional when H is 0 is functional. I mean, anyway, this is the type of operator I'm going to consider in the following. But already the case P less than P equals to 2, it's interesting when I have a nonlinear operator. Because you cannot, there's no associated linear or sublinear operator according to the things that I was describing before. Okay, the classical distributional formulation reads as follows. Okay, you formally test by pi, you integrate by parts, and then you get this guy. So a solution is something which belongs to, which satisfies this equality for every possible choice of the test function phi. Now there are related properties. The basic issues are the following. Since in elliptic theory you essentially want to get energy estimates, so estimates for the gradient, usually you do this by testing by something which is proportional up to truncation's powers or whatever, but proportional to phi. Can you do this? Because the right-hand side is a distribution. So when can you do this? When this is of course linked to the fact that you have a solution with a certain degree of regularity. But then you have to have a solution. So where do you find U? And in fact, these things are related, because assume that you can test by U. Then if you can test by U, you get energy estimates. And then monotonicity methods or graduating or whatever, approximation methods, give you a solution which is usually in W1P. On the other hand, if the solution is in W1P, then you can test it, because it satisfies duality. So these two things are related. So from now on, I will call a solution which is in W1P an energy solution. Usually this is possible when the right-hand side is in the dual of W1P. When it's in the dual, then monotonicity methods apply. You can test by U, you can find U in space. And this is called energy solutions. So energy solutions are solutions which are in W1P. So the energy is integrable enough. On the other hand, observe that this is not the largest space for which this formulation makes sense, because these guys goes as due to the p minus 1. So if you just allow same infinity stuff, this is bounded, and you can just consider these guys. These are called very weak solutions. So distributional solutions which are not in W1P are called very weak solutions, and they actually exist beside the usual ones. They are more pathological and also more natural. It depends on the way you look at them. So. And therefore, in the rest of the talk, I will distinguish two regimes. The first regime is when H is in the dual, therefore you find energy solutions. And the other regime is when H is not in the dual, and then you find you deal with real very weak solutions. So in the first part, now I will deal with the case when H is in the dual. In this case, you can write it down in this way. So I will consider this prototype example. So the first result I know in this direction is due to invariance, and it's as follows. Tadeusz invariance, of course. It's essentially the same result I was talking about before when P is equal to 2. Otherwise, you get this guy. So observe that the gradient is dimensionally speaking exactly what F is once you simplify divergence. Okay, is anybody noticing the difference here between the linear and the nonlinear result? There's one detail that doesn't make this the perfect analog of the linear result. So in the linear result, you get p equals to 2. What's the difference? So the difference is that you get 2 here, while in the linear result you get 1. 2 larger than 1. So you should get p minus 1 here. And in fact, p minus 1 is the largest range for which this distributionally makes sense. And this is an open problem I'm going to come back on later. But observe that when Q is not in LP, then this guy doesn't belong to the dual. So in the dual range, this is the largest range. It makes this guy belong to the dual. Di Benedetto and Manfredi then extended this to the case of systems, proving that the effect is in DMO, then the gradient is in DMO. DMO is the space I was talking about before. Oh. Okay, then Caffarelli and Peral. Let me spend a few words on the technique by Leibniz. So in the linear case, what do? You get a linear representation formula, and then you go for singular integrals. Here, this is not possible because the problem is non-linear. Therefore, what Leibniz did is to replace the use of fundamental representation via fundamental solutions by local energy estimates for homogeneous equations. Because local energy estimates are of this type in this case. If you get this equation with the right-hand side equal to 0, then you get that, for instance, the sup at infinity over a ball, PR, is controlled, modulo universal constant, by this guy, the average over the ball 2R. So what's this guy? This guy is 1 over Rn R dV. And so this is exactly the homogeneity of a singular kernel. So this plays locally the role of a representation via fundamental solution. Since this is only local, you have to match up then globally, and then instead of using singular integrals, you use maximal operators, actually sharp maximal operators, those considered by Pfeffer and Stein. So you're not using the singular integrals, but you use those tools that are typically controlling singular integrals. So it's a replacement. Oh yeah, then Caffarelli and Peral gave another approach to LP estimates in the setting of homogenization or nonlinear homogenization problems, and then can be used to get another proof of this type of results. And then Kridov, in a series of papers, also employed maximal operators, this time sharp maximal operators, to get parabolic estimates in certain mixed norm spaces. And then there's a lot of people who devoted themselves to extend that type of results. There are several people here. I don't think that is on stage. Okay, Leibniz result extends to general equations under the assumptions I was telling you before, but not to general systems. It only extends to systems of Pilot-Laschen type, so when the nonlinearity is in some sense quasi-diagonal. So this is nonlinear, but the nonlinearity is due to the fact that you're taking the linear part and you're perturbing it in a diagonal way, is something which is proportional to the modulus of the grid. The Pilot-Laschen operator is typical extent. Instead, it doesn't extend to general systems, because general systems behave themselves bad just because they are systems. In fact, there's a fundamental result of Streff and Yang showing you that there are unbounded solutions, even when the right-hand side is 0. So this, of course, rules out the possibility of getting the result, because if you get the result, then the gradient is in LP, and it's almost Lipschitz. Well, this tells you that you will unbound. This is typical in the case of systems, because in the case of systems you have many components, each of them can concur to satisfy very different equations. So if the equations are not too much correlated, as in the diagonal case, you can satisfy some equation somewhere, creating singularities elsewhere, just by topological reasons. Oh. Okay, the parabolic analog of Leibniz result has remained an open problem for a while. Essentially for a few reasons I'm going to explain now. And it has been settled only recently in a paper by Giuseppe and myself, where we prove essentially the same result. Apart from this borderline, from this case, which is from this lower bound, P cannot approach 1, and this is optimal. So you get essentially the same analytic result, but with the additional assumption that you cannot get rid of, because otherwise solutions are, because the result is otherwise false. In fact, let me briefly explain why the result is false when P is too close to 1. This guy is less than 2 close. Just consider the homogeneous case, and let's ask what am I proving? I'm proving that the gradient is integrable, and sometimes the gradient cannot be too large. So the bad case is when the gradient is very large. Okay, now P is less than 2. So when the gradient is very large, this is very small. So this kills the diffusion. And since the regularization properties of the operator are linked to the diffusion, there's no diffusion enough to compensate the evolution. So there can be a fast developing of singularity because there's no diffusion, essentially. So when P is too close to 1, there's no diffusion enough to compensate the evolution, and you can have bounded solutions. Okay, in this case, the idea is to completely abandon the use of maximal operators and of any other harmonic analysis tool. Why? Essentially because they just do not work. Let me go back just to understand a bit better this equation. Let me just tell you why they do not work. Okay, the technique of invariance of Caffarelli, Krylov, and whatever is linked to the possibility of getting homogeneous estimates. These are homogeneous estimates, and they play the role of local representation formulas. Okay, the question is, can you get homogeneous estimates for that equation? The answer is no, because this equation is not homogeneous. So if you multiply u by a constant, this doesn't satisfy a singular equation. Because this guy's k is like p minus 1, this guy's k is by 1, and so there's a deficit scaling of p minus 1. So this completely rules out the possibility of getting homogeneous estimates. So you have to recover homogeneous estimates. And in this case, you use the so-called Di Benedetto's intrinsic technique. Di Benedetto's intrinsic geometry technique. So the idea is that this is bad, while the good case is this guy. Because then, if I go to the heat equation, I can consider the so-called parabolic cylinders, which are objects of this type. This is the usual Euclidean ball, while this k is like rho squared to compensate one missing derivative here, and this is okay. So how can I reduce this case? Okay. So the idea is to consider intrinsic cylinders. So I add an additional parameter here that I call lambda. Lambda is 2 minus p. Let me just consider the case p larger than 2 for simplicity. Okay, this is the cylinder I want to consider. And moreover, I do require that on the same cylinder, the gradient is more or less like lambda. And observe that this is an intrinsic fact, because lambda appears here. And appears here, but assume that this works. Now, if this works, this tells that the gradient is like lambda. But if the gradient is like lambda, I have this guy here. But if I have this guy, I have the Laplacian here. And if I scale back from this cylinder to Q1, then I get this equation. The idea is to employ intrinsic cylinders to get homogeneous estimates and to go on. Of course, this is difficult because it is not immediately clear how can you satisfy a different case the intrinsic conditions like this. So what we cooked up was a completely different way of proving these estimates. We avoid maximal operators, and we just have a purely PD proof of this fact. What we do is we proceed with an x in time argument at every level. So we want to prove that the gradient is integrable, so you want to study the decay of the level sets of the gradient. So let's say level set and level lambda. And so you take the level set, you make an exit time and a counter and signal decompositions with these cylinders. So every lambda determines a new metric, and therefore new intrinsic cylinders. Then you do exit times, and then you go on. So you have a completely elementary proof of this fact. Where did I put right. And this is a summary of what I was saying. And the result extends to general equations, of course, and to systems too. So in turn, you can go back and you can get essentially new, let's say, more elementary proofs of the previous results in the elliptic case. And going back even to the original theorem of Calderon-Zingel on singular integrals that can be proved, for instance, now directly without much intelligent interpolation theorem. In particular, you can also give a new proof, as I was informed. I'm not sure about this, but I was informed by some people in Korea that were giving alternative proofs of basic results of Nonlinear. And in particular, if you go back to the previous result I was telling you before, then you can get proof which just stays in one page, because it's just based on Vitalis covering mean-value properties of harmonic functions. So essentially, you can give a fast approach to Calderon-Zingel estimates, which is now very elementary. Okay, I will end up this part that considers the dual case, just going back on the open problem I was talking about before. So, this is the linear case, and this holds for every q larger than 1. So you would like that for this case, this would hold for every q larger than p minus 1. But this is an open problem that no one is able to tackle up to now. Essentially, it's very remote, and it is linked to several other basic facts of complex analysis, harmonic analysis, places like formal mappings. Very basic issues here. And let me observe that this is the largest range for which this distribution solution makes sense. Essentially, because when the gradient is in p minus 1 and f is in p minus 1, you can still test by smooth functions and get something which makes sense according to the duality. The only result available up to now has been obtained by Ivanitsyn, Bourdon, and in different form by Lewis, and tells you that you can get fixing proper boundary values, for instance, a priori estimates, in local a priori estimates, going a bit down. You like that this epsilon is 1, with a strictly inequality, of course, but you can just go down on a small epsilon, which is universal. It doesn't depend on the solution, it just depends on the operator. And this is very difficult. And a parabolic version of this has been done by Mingione and Lewis in two very interesting, extremely involved figures. They are very interesting. So this is the status. This is the current status for the subdual case in divergence form structure with respect to the right hand side. So this last result leads us to the next part of the talk. Well, I'm going to talk about the cases where you are below the duality exponent. So the right hand side doesn't belong to the dual. So what is known is I'm going to talk about again same operators, and for simplicity I'm going to talk about the case p larger than 2. I'm restricting to this because otherwise when you go below 2, then measure data, then you have to add more definitions. There are certain cases where solutions you're considering are not even in sublab space. This can be fixed in a way, but it's too long to be reported here. So we'll consider this regular problem with finite mass, and the linear case is a classical result of Lippmann, Steinbach, and Berger. Nowadays you can approach the linear case in many ways, but I'm interested in nonlinear case. In the nonlinear case, first of all, how can you find solutions? Essentially, in the most natural way you might imagine. You take the right-hand side mu, you smooth it out in a way or in another, you just truncate it, for instance. Then you solve these problems. Then you can pass the limit. Then you obtain solutions, which are solutions obtained by limiting approximations, and this justifies the acronym. This has been done by Bocard and Galouet. I mean, it's a natural thing to just reduce to more to smoother problems. You solve them, and then you pass the limit. Essentially, monotonicity methods going this way, like Galilean methods, reduce to finite dimensional spaces. That's the same. So the solutions I'm going to talk about are these ones. And there are particular solutions that are not any distributional solution. These are solutions which are obtained by a limiting procedure. So they are supposed to be better than any general distributional solutions. In data, you can prove it better. There are then other solutions for instance, the normalized solutions as introduced by Del Maso, Murat, Rossi, and Beignet. And what's the name of the other solutions of that we normalized? The ones you were
there are
entropy solutions. Okay, anyway, all these solutions are strictly related to each other. And in fact, there's a very interesting result of Kirpelan and Kusi and Puy and Paya that prove that all these solutions, okay, it's difficult. And Tuola, they prove that all these solutions are equivalent in the case of when the measure is possible. Otherwise, I would refer to this basic paper of Del Maso, Murat, C. and Beignet for more on the existence and comparisons. But anyway, in a way or in another, when you have to show that one of such solutions exists, then it's always the approximation. So I will talk about solutions. I will talk about those solutions that we certainly know they exist. Okay, actually there's one case where, okay, let me tell you that these solutions are not known to be unique, because of course here it's up to a subsequence. Like compactness. So you could, in principle, have two different subsequences converging to two different solutions. And it is not known that you approach always the same object. In fact, there's no, the uniqueness problem for measured data is open, and there's no known function class where it's uniquely solvable. So this class provides uniqueness when mu is in a 1, where mu has certain capacity conditions, but not in general, so it's not known. And this is not a problem I'm going to go through now. I'm going to talk about a priori estimates. Actually, that's one case where solutions are known to be unique. And that's in some sense the critical one when the right-hand side is a zero. It's very bad because you can concentrate the measure at one point, so you might allow the solution to be worse at this point. But geometrically speaking, it's simpler because you just consider one point as an equation. In this case, this is the unique solution. It's called nonlinear Green's function, just by analogy with a linear case. And of course, you cannot get other solutions by convolutions with this, but it's still called a fundamental solution. And it's useful because then you can test the optimality of your results by comparing with this guy. Okay, the basic Calderon segment theory has been fixed by Bocard and Galois. They prove exactly that every solution is exactly in the space within the boundaries fixed by the Green's function. And then when Q is larger than Q is larger than 1, then you get this. They perfectly go back to the linear one, so easy. Actually, the case, the vector case has been, the vectorial case has been fixed by Wilson and Muller, who also fixed the case B equals to 1, which was rather delicate, which needs different proof, because some of them embedding makes problems when you are working on this. Okay, this is the lower order Calderon-Zygmunt theory that tells you about the integrability of the gradient. And now we go to the higher order Calderon-Zygmunt theory. That is the following. Since you get a second order operator, it would be natural to get some more differentiability of the gradient. So to get regularity beyond just integrability of the gradient. And so now we briefly discuss this. So where can you find the gradient other than in empty spaces? It is known that already in this very special case, you cannot show that the gradient is in W11. So where can you find the gradient? So the idea is to fix this by considering so-called fractional solver spaces. So fractional solver spaces are spaces where the rate of differentiability is fractional. So this is described as following. You want to measure the oscillations of V rather than L infinity in the L gamma norm. And you want to say that they are small enough to compensate the blow-up of this kernel. So observe that the larger S is, the worse this guy becomes, and therefore it's more difficult to satisfy this. From a scaling property viewpoint, you might imagine for the sake of intuition that this behaves as really a fractional object. So the idea now is that you cannot be in W11, so where can you be? And you actually, let me start by the case P equals to 2, and you are in every space before. So if you cannot be in W11, you are in every space before. And the point is that this guy is nonlinear. Yes?
You should have W1 minus P with P dependent on epsilon.
I also have that. Yeah. That is, you can increase this guy, and you can decrease this guy according to the interpolation embedding. But you see, I prefer this because in this sense, since I'm interested in differentiability, I want to optimize the differentiability. So I get but your remark is, in fact, I think that in the original paper, this is exactly the formulation. And in fact, in my original proof of this, of course, what you say is that, okay, what Luke is saying is that by fractional embedding, this embeds into a space with a larger integrability and weaker differentiability, and this way it's fractional solver space. If you look at the proof, this gives the whole range independently of the embedding. So you can even avoid the embedding, it gets you everything. I prefer formulating in this way since now I want to optimize the differentiability range. Thank you. Okay, so you cannot be in W11 and you are in every space. Okay, what about the case P larger than 2? Take for granted the first line and apply this to the fundamentals, to the gradient of the fundamental solution, just by minimizing the integrability range P minus 1, because you want to maximize the differentiability 1. And then you come up, the gradient should be in this space. So this is for the fundamental solution. Actually, this holds for every solution. For P equals to 2, you go back to the previous results. And this is shown in the sense that you cannot allow here epsilon equal to 0. Observe that this is less than 1. Okay, why fractional? Because already in the case of the p Laplacian operator with 0 right-hand side, due to the degeneracy of the equation, you do not get always second derivatives. You get fractional spaces. And in these terms, you lose the fact that you are approaching 1, let's say an integer here, but you go to a fraction anyway. Also, this is optimal. And this is optimal. Okay, there are factor results in this paper of mine. This is optimal in the sense that these fractional solver spaces, as Luke was pointing out, they have a fractional embedding. This is the limiting embedding of what you were talking about. Say when you allow 0 differentiability and you go to the maximum. And if you assume this, then you come up with this, and this is false for the Green's function. So you cannot allow epsilon equal to 0. So in some sense, this result gives the maximal regularity for solutions of these problems. This is the maximal regularity for measured data problems. Now we go to the last part of the talk. I'm going to talk about very classical stuff, linear and nonlinear potentials, because I would like to present a more drastic analysis of Calvin-Zimmermann results. Please let me recall you that for these basic equations you have these two estimates. So you can bound U by the I1 risk potential. Okay, you can consider, of course, n larger than 2 and 0 at infinity as a solution. Then you can bound U by the I2 risk potential pointwise, and du by I1. So these are pointwise estimates. So they are apparently very much linked to the structure of the problem, and you would imagine that no analogies are allowed from here, but in this part of the talk I would like to present completely sharp analogs of these results in a nonlinear case, in particular to the p Laplacian operator. Let's go on. Okay, I'm going to talk about local estimates. So from now on, the risk potential will be this object for us. This is called the truncated risk potential. It's particularly suitable to local estimates. It's just another way to write down the risk potential. It's just a dyadic decomposition that shows you that this is controlled by the usual one of the whole Rn. So from now on, this is the This is the new risk potential. Our risk potential is this guy. And so now the goal is that for p equals to 2 general nonlinear equations like this, and for p larger than 2 general nonlinear equations whose model is given by the p Laplacian operator. Okay, we'll consider case p larger than 2 for simplicity. Let me observe that when p is larger than 2, these estimates are not true, of course, because they just do not respect the scaling of the equation. If you get an equation like this, then if you scale mu by c, then you have to scale this by c to the 1 over t minus 1. And in fact, if they would be true, by a scaling argument, you would come up with every solution c. Because they simply do not respect the scaling of the equation. So these estimates for p larger than 2 are not possible. And therefore, you go on and you introduce the so-called nonlinear Wolff potentials, and these are nothing but the risk potentials incorporating in a nonlinear way the deficit, the deficit exponent of the equation, 1 over p minus 1. 1 over p minus 1 is the thing you have to consider when you scale the equation. Now you put it inside, and you get a new nonlinear potential, which is called Wolff potential by from Tom Wolff. Actually, these potentials were firstly considered by Having and Mazian, who proved a certain bunch of important estimates. Then they left one case open, and then had Wolff fixed this case. Very interesting paper by the end of the 70s. And for p equals to 2, they go back to the risk potentials. So these are Wolff potentials. They are more or less ubiquitous in nonlinear potential theory. They are used to prove nonlinear analogs of the classical linear criterion. Delicate fine properties of solver functions and whatever. They play the role. They fully replace risk potentials when you go to nonlinear settings. And the breakthrough result has been given by Kipelainen and Mali, who showed that, for instance, for more general equations, but just let me concentrate on the model case, you can bound pointwise u by this Wolff potential, which is given by this. So in particular, when p is equal to 2, you go back to the usual estimate. This additional term is a constant, is irrelevant in some sense. It must be there because this is a local estimate. So think of Laplacian of u equals to mu, and you multiply u by cut alpha with the additional terms. It must be there because when I goes to 0, this goes to 0, it's finite. So you get u less than or equal to u. Otherwise, q plus infinity, this disappears provided using the program. And this is sharp in the sense that when mu is positive, and u is positive by maximum principle, you can also put the Wolff potential here. So this tells that there's a double-sided estimate that makes this estimate sharp. You cannot improve that. So there's no alternative potential whatsoever that improves this estimate. Because essentially you go to the p Laplacian, so Wolff potentials come into play. And then there are, then there have been a lot of work. Trudinger and Wong gave another proof of this result, and they also extended to subelliptic settings. Labutin extended this estimate to the so-called K-Hessian equations. These are certain fully nonlinear equations that they interpolate Laplacian and Monchapin operator. They are essentially fully nonlinear equations which are based on the symmetric intermediate functions of the eigenvalues of Hessian. And then finally, there's a new interesting approach by Kurt and Goose again that proves this. Okay, this is as far as the estimate for u. So the estimate, an analog for the gradient, as being an open problem for a while, and has been believed to be false because actually this is a double-sided estimate. For the gradient, it's not true. They didn't bound this. So the gradient can be bound from below by a Wolff potential. So it remained open until the first case was. Okay, let me tell you why. Let me tell you why this estimate is important, for instance, from the Calderon-Zygmunt viewpoint, because essentially it realizes the interpretability theory of solutions. If you want to know when solutions is in a certain space depending on mu, The behavior of Wolf potentials is known because they can be controlled by this iteration of risk potentials. This is a nonlinear iteration of risk potential. This is an inequality that has been proved by Avin and Matia. In fact, the name of Avin and Matia potential stems from this paper. Therefore, you know the behavior of risk potentials, and you know the behavior of Wolf potentials. Therefore, if you want to know when the solution is, you go by the Wolf potential by this estimate. So you just forget about the equation. It's just as in the linear case. You just look at the representation formula and that's it. But this is just one example. Then, for instance, Gilpin and Mully proved the linear criterion using this estimate. Gilpin and Kusier swore, right? Proved these equivalence of solutions using again this linear potential. You can prove several things. Essentially because they play the role of the convolution with the fundamental solution. Okay, the gradient estimate has been remained an open problem for a while. It was believed to be false, essentially because you do not have a gradient, a double-sided estimate for the gradient. Although I believed it was true, and luckily enough, I was asking because I was not from this field, and I had the conjecture that it should have been true, because I had previous work on some things related. Actually, I spoke to some expert, and I got negative feedback in the sense that it was not completely convincing it was true. Anyway, I was convinced it was true, and it finally was true. And the first result in this direction is by me, and tells that you can just bound the gradient by risk potential as in the usual case. And the estimate for the gradient is more difficult because, for instance, you know, if you want to bound the gradient, this includes uninfinity estimates when u is equal to 0, or when u is very good. But usually gradient estimates are done by differentiating the equation. But in this case, you cannot differentiate the equation because the equation involves a measured data, and the a priori estimate is a measured data set. Eventually, the first proof was that I was taking the solution, I was taking the equation, I was differentiating it in a fractional sense, getting Kachopolis and inequalities and energy estimates in fractional space and having a fractional version of the Georgi equation. But anyway, this is the first result. Okay, in the nonlinear case, the first result has been obtained by Hutzer and myself, and it has this. So once again, you go on to nonlinear Wolf potentials. And this was believed to be the optimal case, because if you go to p Laplacian, then you have to go to Wolf potentials. But actually, I had a conjecture for a certain while that this is yet not the best thing you can do, because when you switch to the gradient, you might argue in another way. And the way you might argue is the following. Consider this equation. Okay, the common way of thinking is that this is a nonlinear equation in the gradient, but you might also view it as a linear equation in a nonlinear field of the gradient. So this is nonlinear in the gradient, but it's linear in this object. And so it's linear in this composite quantity. Since these equations are inverted by Riesz operators, then you might think that there exists a linear estimate, not for the gradient, but for this guy. For this guy. And then the conjecture was that this is true. Observe that the same argument is not possible when you think of u. Because when you think of u, there's no way to consider this as a linear equation of a nonlinear object of u, because there's a gradient. You have to invert the gradient. You have to pass the integral. So that, and that's essentially the point while Wolf potentials are optimal for estimates on solutions. Okay, in other words, what I'm talking about here is to decouple the problem in this way. At the beginning, it seems to be crazy to decouple the problem in this way, because this is always solvable, but it's solvable in infinitely many ways. In particular, you're not sure of finding a solution of this form, of this special gradient form, and of the gradient you are interested in. The solution is targeted. Nevertheless, with Tuomo, we were able to prove this estimate, which was rather surprising. So the estimate tells you that no matter the problem is nonlinear, you can bound the gradient via the risk potential, just putting this guy here. And this completely, we covers essentially all the estimates for these equations in the last 20 or 30 years. Because essentially, you do not have to go to the equation anymore. You just look at the risk potential as it was the usual Poisson equation. This actually holds for every equation. And with Dini continuous coefficients, and Dini continuity is a minimal assumption under which this works. Why? Because when u is 0, this gives an infinity bound for the gradient, which is not true if the coefficients are not infinite. So in particular, there's a complete unification of the theory of general possibly degenerate elliptic equations, Poisson equations. There's no difference up to Lipschitz continuity, and you get this pointwise. Even more surprise. Okay, for instance, when you are in the whole Rn, you get just visualized by passing out plus. So this works for any equation. In particular, all the results for the last 30 years for this equation, used by several different techniques, now they all follow from this estimate, because now there's no, you do not have to go to limit this anymore. Even more surprisingly, we also proved the following thing. So let me write down the definition of the risk potential here. The definition of the risk potential is this guy. This is the front here, risk potential. This is integral from 0 to r, mu b rho x rho to n minus 1, b rho over rho. So if you assume this is an integral, right? So if this is finite, when r goes to 0, this goes to 0. If this is always finite, this goes to 0 at every point, and this tells you that the gradient is bounded. But in particular, now assume that this guy goes to 0 uniformly with respect to x, then the gradient is continuous, because you are, in some sense, this uniform, in fact, excludes the formation of singularities somewhere. And so, this tells that there's no difference between Laplacian and P-Laplacian or whatsoever operator up to this one regularity. And this is quite striking because the operator is degenerate. Because this also extends to general equations. So there's a, up to now, this theorem, this paper essentially unifies the linear and the nonlinear theory up to one. In particular, a corollary. If you are in a Lorentz space Ln1, then the gradient is continuous. This is a classical result for the Laplacian. The Laplacian is classical that, and also for the P-Laplacian, I mean, if what it was known was for this, I mean, for the Laplacian was classical, for the P-Laplacian, maybe for some experts will know that if you are in Ln, the gradient is not bounded. If you are in Ln plus something, the gradient is Hilbert continuous. The borderline case is given by this Lorentz space. It's a space which is an interpolation space, and then the gradient is continuous. This is just a corollary at this stage. It follows this as a corollary. Okay. Additional results involve the parabolic version of these results, and this is very non-trivial. It's highly non-trivial essentially because the philosophy of this result is that you want to decouple the equation from the right-hand side. You just go to the potentials. In parabolic problems, so you want to forget about the equation and the solution, you just look at the potential. But in parabolic problems, you have to link solutions and poles you are using in intrinsic geometry. This means that you have to consider intrinsic potentials, but then if you do consider intrinsic potentials, you are coupling once again potentials and solutions. So there's a way to decouple, and that's what we did with Tuomo, with me here. And moreover, we did the same result for fully nonlinear elliptic equations. Essentially, we proved with Totti Daskalopoulos and Tono Busi that if you get a fully nonlinear elliptic equation, and so you want to consider the best space, okay, the larger space where f has to belong to, in order to guarantee that the gradient is continuous, and this is once again L1, Ln1. And this is for fully nonlinear. So this is just some other things, some other shots of the things we're doing. Okay, finally, let me just observe one thing. A classical integrability theory and the Giorgi's theory go back to when Okay, extends to measurable coefficients, also the results of Bocard and Dunway, and extends to measurable coefficients. When coefficients are measurable, this estimate cannot be true, because the estimate would imply an infinity bound for the gradient, which is false when coefficients are measurable. Actually, there's there's an analog. Okay, what's the maximal regularity where coefficients are measurable? The maximal regularity is the so-called higher Gerring's integrability. So the solution is known to be in W1P plus delta. So it's a bit better than W1P. So this is the best you can get. So if you want to have an analog of these estimates, this analog must stop at W1P plus delta. This parenthesis tells you that this is an open interval. So there's no pointwise estimate. There cannot be, because this is based on reversal inequalities which are self-improving, so there cannot be a closed interval point. And actually, even the best integrability exponent is not known, as I remember. Okay, so this is the best thing you can do, and therefore, what you can prove is no local analog of the estimate. This is rather involved in the formulation, but look here. This is the maximal operator of the gradient. This is the usual maximal, the little maximal operator. Forget about it. Just consider the gradients, because if you can bound the level sets of the maximal operator, you can bound the level sets of the other gradient. So you can control the level sets of the gradient by the level sets of the potential. And if you would only have this would be implied by the previous estimates. But then you have a correction term with a constant that tells you that the best estimate you can get from this equation is up to p plus delta. This is exactly the delta I was talking about before. How do you observe this? You just multiply this by lambda, you integrate, and you observe that you multiply by lambda to the q minus 1, you can reabsorb this guy only if you are considering the space, a q, which is less than p plus delta. In particular, this is a no-local analog, and this implies exactly this. The gradient is in the same space of this risk potential, as long as x is larger than p plus delta. So once again, this things follow, and essentially this is a nonlinear analog of the classical result by Adams. So, okay, I think I'm finished, and I would like to thank you with, usually I finish my talks with teachers or a friend of mine who's an artist. Thank you.
Do you have any questions? So tomorrow is the dark side, so...
Tomorrow for the dark side, right.
Okay. Thank you, sorry.